Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. I am going to take a look at our raycasting today. We actually aren't running that poorly. If you take a look at where we're starting, it's actually not that bad. I thought we were going to be worse off than we were, but when we actually made the bounds of our lighting solution a tighter fit, if you will, for what we were doing. So if you look on here, I forgot I haven't actually run. Oh, actually, do I save this? I probably saved this. Let me open it. I should mention that we're trying a new version of Remedy today that I have not tried yet. Let me go ahead and load that up here. There we go. Yeah, there we go. So I was about to say some stuff about Handmade Hero, but I'm actually going to pause and say what I really should be talking about first is the fact that we now have version 3 of Remedy, which is the debugger. And I don't know, for those of you who have followed the stream for a long time, you know that we used to use Visual Studio for debugging. That was because it's just a better human factors debugger than pretty much anything else you can use at the time on Windows. It's not a good debugger, but it's good at displaying information, and it's good at quickly restarting your program. And it basically had all of the good user interface that you would need by comparison to other debuggers on the platform. So that's why that's what we were using when we started Handmade Hero. Now, in that way that Microsoft generally, pretty much exclusively for the past 20 years, only ships worse versions of their software each time. So if you were using, version 5 and you get version 6, it's worse than version 5. And you get version 7, it's worse than version 6. Sometimes it gets dramatically worse, like Windows 7 to Windows 8. Sometimes it's only slightly worse, like each update of Windows 10, where it just gets, a little bit worse each time until, eventually it's gotten dramatically worse over the course of several updates, etc. So Visual Studio had been decaying for many years. The last really good, not even really good, but the last version you'd probably want to use was 5. 6 was okay. And then everything after that, so 2005, 2008, and so on, have just been getting really bad. And now it's really pretty bad. It's very slow. It has a lot of bugs in it. It's bad. It crashes a lot, and so on. So we had kind of been struggling with that, and I had said multiple times on stream, I'm like, somebody needs to make a debugger to replace this thing. It is garbage. And not to mention the fact that installing it is a huge chore. It takes, oftentimes the installer just fails. You get inexplicable errors that don't work. You have to create a Microsoft account to install it, even if you paid for it. It's a disaster, and it installs SQL Server on your machine. It's unfathomably bad in terms of the installation process for a debugger, right? Because you can only get it as part of the IDE, and the IDE has all kinds of crap you don't want. So eventually, actually somebody, and it's X13 Pixels on the chat, was like, all right, I'm going to do something about this. And they started writing a debugger, and eventually they actually got it good enough, 1.0, and we started using it on stream, and it was missing a bunch of features, but it was just plain better to use than Visual Studio. And it's Remedy BG, it's this debugger right here. And we just started using it, and it's super fast. It steps and updates the watch window so much faster than Visual Studio. It's got the same kind of clean, easy to use systems that Visual Studio had that made it preferable, where you can just quickly do what you want and you don't have to wade through tons of command line parameters and hard to view windows. It actually shows you what you need to know when you need to know it. But didn't have all of the crappy baggage of Visual Studio. It's one exe. You can literally just copy the exe onto your machine, and it works. It loads instantly. It runs instantly. It's great. And then steadily since that version 1.0, it's just been getting better and better and better. Now, in this version 3, which we've just upgraded to, and X13 Pixels in the chat can correct me if I'm wrong, but I think he actually did something that I literally don't know if any debugger has ever done, and it's kind of a breakthrough feature for people who use this. So I'll describe what it is. Correct me if I'm wrong, X13. Conditional breakpoints were added in this version of the debugger. So a conditional breakpoint is like if you have a breakpoint and you want to change it so that it only happens like sometimes, right? So you want to say, look, I'm going to type a piece of code in here, you know, like, if x equals 5 or something, right? If you want to do conditional breakpoints, obviously that requires evaluating C expressions while your program is running, because every time you go and hit that particular breakpoint, traditionally what was done in, say, Visual Studio is it would actually use an actual breakpoint. So it would, you know, use an int3 or something to actually stop the code when it hit there. It would then branch to Visual Studio, which would actually go run its expression evaluator. And then if the expression evaluated to true, it would then actually break the program into the debugger, meaning it would show you that break. Otherwise, it would just resume, right? So what that means is that anytime you ran with conditional breakpoints, you got a massive slowdown, because every time it hit that breakpoint, it was going to have to do this whole process. Well, I believe what X13 Pixels did, and correct me if I'm wrong, is actually it compiles the actual expression into your code, like into your executable, and jumps and patches that with a jump. Am I right about that? Let me check. Didn't end up doing that. So how is it so much faster? Okay, I take it back. So X13 Pixels tells me, because it's 15 times faster than Visual Studio. And so I assumed he was actually trying to do that. But because he had talked about doing that before, he's saying that it's actually just 15 times faster, even doing it with the interrupt. Wow, okay. So I take it back. I guess he didn't have to do something no debugger had ever done before. He just actually, I guess, wrote much better code than the Visual Studio team and is 15 times faster. So, all right, I guess there's not much point in doing the compilation thing, although maybe if you have enough threads there is. I don't know. Anyway, never mind. So, separate from all of that, it's 15 times faster than Visual Studio, which means that now you can actually use conditional breakpoints in places that probably you couldn't really use them before. Because previously, you know, if you were trying to set a conditional breakpoint on something that got hit often, it was not really plausible to do that because Visual Studio would run so slowly that you would really want to try to avoid that if you could. I mean, if you had to, you could, and you just kind of let it sit for a while, but you wouldn't, because 15 times slower is a lot slower, right? If something would have run for a minute before, it's running for 15 minutes now, right? And that's, you know, not great or whatever, right? So Remedy now has really fast conditional breakpoints. And I feel like that's kind of a game changer for people who use breakpoints a lot with conditions on them. I don't actually do that. But for example, John Blow talks about this. He uses them all the time. So for people whose workflow relies on conditional breakpoints, Remedy 3 is going to be a huge deal for them. Like a huge, huge deal for them. For us, I don't know that 3 is all that important to us because we don't actually need conditional breakpoints. I don't tend to use them. Probably I should. And maybe I will now that they're so fast. But either way, Remedy for us, like just the 2.0 branch was a huge win. Like we... use it all the time on stream. I use it as my pretty much only debugger at Molly Rocket. It's been a huge, huge, huge win. And so anyone who hasn't been looking at Remedy because it didn't have like all the features that you needed, I would really highly recommend checking out the 3.0 branch as it develops, because there are a lot of features in Remedy BG right now, and it may have crossed that threshold for you where now it's got everything you need. And man, if it does, switching to it over Visual Studio or Visual Studio Code or any of the other like things that people have been using for debugging Windows is a massive, massive, massive win. Just being able to do single step as fast as you want, like you can hold down the single step key and the watch window just updates accurately the entire time. There's nothing else on Windows that does this, right? I mean, you look at Visual Studio Code, it doesn't even update at all when you do that. You have to let go and wait, a second, and then it pops in or whatever. It's just way better. So I would really, really highly encourage everyone to check this out. It is not expensive. I think you can just literally type remedybg.itch.io into your web browser of choice, and it is literally $30, and it will be the best $30 you've ever spent. If Visual Studio or something is bringing you down, it is just way, 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 way better. So highly recommended. I don't know if the 3.0 branch has settled down completely yet because it just came out. So I don't know much about that, but at the very least, the 2.8 branch, which you can also be on if you want to, has been very stable for me, the latest version. 3.0, I don't know if it needs a little time to settle down or not. We haven't used it. It may already be completely stable, but even if it's not, the 2.8 branch is completely stable for me. That's what I use. And 3.0 will be there soon enough. So, either way, check it out. Both versions are up there. We'll be playing with the 3.0 branch and kicking the tires, so you can check it out on stream, obviously. But I would really encourage people to get on there. There's a GitHub that has an issues list. So if you find bugs, get them up there. That's the way it gets better, by people reporting problems. So, check it out. But I think it's something that should be on every programmer's machine at this point. If you program on Windows, it saves you so much rage compared to using Visual Studio or Visual Studio Code. All right. All of that preamble aside, let's take a look at Handmade Hero. Basically, the performance level of Handmade Hero right now is actually pretty acceptable, which was surprising to me because we're now doing fully ray trace lighting on the CPU, which normally you wouldn't really expect to be running this quickly at the stage we're at. But I'm pretty happy about everything we did to it. We did a really good job. There's quality issues we're going to want to address. We haven't done a quality pass, so a lot of things in here, including some feedback loops, making the edges a little rounder of the voxel interpolation, getting the occluders to be set correctly for bounces. There's a lot of stuff like this that we have to do, and that'll be a secondary pass, maybe starting a weekend or two from now. And that's just visual quality and a separate thing. Right now, all I really want is I want to be able to do just a due diligence pass over the performance right now and make sure that it's up to at least a reasonable level. And so we're going to take a look at that. Our current performance metric, if we look at it, we're running at around 30 milliseconds. If we take a look at our actual thread performance, you can see that actually if we turned off debug, we'd get some of that back. In fact, you can see like even just the act of printing out like lots of text, for example, the debug system slows things down quite a bit. So if we actually take a look at what we're getting for our speed here, it's more representative of this number. So we're edging in on 60 frames a second, even with the CPU side ray trace lighting, which is pretty great, and something I'm pretty happy about. I don't really understand why I'm not seeing. Did we look into something? So there's a little bit of weirdness here. Oh, you know why? I know why, never mind. We're actually not timing the separate thread parts anymore. That's why we're not seeing any thread behavior out here. That's actually why. We probably can add something back in when I think we probably should for that real quick. That wouldn't actually be a slowdown. If we just time the actual... if we timed the actual thread dispatch themselves, I think we would get that. Although, well, you know, I guess not necessarily, now that I think about it. That isn't actually the case. So, because we split up our slices, the only way to really do it is to put a time in here. And the reason that's a little bit iffy is because the... Is it not timed function? Oh, it's just, the reason that's a little bit iffy is just that if you take a look at how many work queue dequeues we do, there's maybe a few too many of those at the moment. And so if you take a look at what happens when we do our timing there, well, okay, no, that's not that bad. 24 is not that bad. Never mind. So if we actually time what our threads are doing, here you can see the work units for the actual ray tracer getting distributed out here, and you can see those being done sort of as separate pieces, right? And so you can kind of see we've got our extra threads here. We got 6 of them. That's because this is an 8 virtual core machine. So you can kind of see here, if you look at the performance measurement for the CPU, you can see what it's doing here. And we are intentionally not using 100% of the CPU. We leave 1 core idle, or I should say, we don't schedule 1 thread's worth of stuff. So if we detect there's 8 cores right now, you're going to have 1 core, which is the main core, that's running the game loop, and then it's got, a certain number of worker cores, and we won't generate 7 worker cores, we'll generate 6. So we leave 1 idle. The reason for that is the operating system needs to do stuff, and also we do loading in the background. There's 2 loading threads that happen here, and they happen infrequently and just basically block on the OS. That's to keep us from like oversubscribing. So we're trying to, not absolutely, tank the machine. That said, when you actually look at what's going on here, you can see we're not stressing this out at all, and I don't actually know why that's happening, but my so my kind of suspicion there is I do wonder if we're getting, if we're actually a little bit blocked just now by the fact that, look, we can't quite hit 60, so we're going to end up running at 30 kind of a thing. We tried to turn off VSync, but you can see that there actually is a fair bit of stalling that seems to happen there. We wait for quite a few cycles in the frame display, and we never really were able to figure out exactly what was going on there. I do suspect that part of that is just because we're running on a streaming machine, and it's locked to stream out the HDMI port while also rendering the screen. So I don't know to what extent Windows's compositor is kind of the thing that's causing us issues there, right? So we're not going to try to attack that part because it's sort of a separate issue from how fast our stuff goes. Our goal really is just to make sure that to the extent that we can, we reduce the amount of time spent in ray tracing. And the reason for that is even if we don't want to actually speed things up at all, even if we're happy with the speed things are, the faster we can make that ray tracer, the more rays we can trace. And you can see there's some flicker in our lighting right now that's like variance. We can attack some of that with sampling, with better, with basically better handling of the samples we collect. So there are ways in the quality pass we'll be able to improve that. But regardless, the more rays we can cast, the more accurate a solution we can construct anyway. So we kind of want that performance either way. So what we, end up with is we end up with a situation where we know that our ray casting is the main, thing that is the main like speed bump that we have for how many rays we can cast. Like this is the thing that makes us have to worry about cranking up the number of rays to, significantly more, let's say, than it was. And so what we really need to be able to do is we need some way of making sure that we're doing a reasonably good job performance-wise inside this code, right? So inside the code where we're actually doing our ray casting, we kind of want to know that we're doing a good job in here. And we want some way of, guaranteeing that that we're, efficient through this this part of the code. Now, there's two parts to this, and we don't really know very much about it quite yet, right? The reason I say there's two parts, you can actually see I've gone ahead last time and split them into two branches of an if. One is doing actual collision detection on the ray and the pieces of geometry in the scene. And that's one right here. So this right here loops over actual blocks, and it collides against those blocks, right? So this piece of code actually records hit tests, and it just, is designed to produce the ray casting against rectilinear volumes that you would expect. So this is very straightforward. This piece of code, on the other hand, is a little bit different. This piece of code is instead just trying to cull volumes using a hierarchy. So this, although it's basically the exact same code, like you can see here that's going to do the exact same thing in either case for the first part, which is just computing a box intersection, it's actually going in and trying to determine whether or not it should go down one side or another of a bounding hierarchy, right? And that's what this piece of code is doing. Now, there's a reason that I separated this out. We made this code generic originally just because that's what we were doing. We made a hierarchy of boxes, and we just said, look, eventually you get down to the bottom, and we say there's, certain number of boxes here or whatever, right? Well, if you look at what happens here, the intersection to try and determine whether or not we hit a particular box and then selecting that box, it's actually quite a lot of code. Now, it doesn't look like that much code, but each one of these v3-4x operations is relatively expensive. If you take a look in the SIMD side of things, I guess. So, yeah. So if you take a look at how this is actually working, if you go and check, just this one. Well, you know what? Actually, here's an easier way to do it. Let me just show you what the assembly language code looks like. Because you can see it gets expanded from here. Let's say you have something like an operator minus that you're seeing there that's just written in the code. It just looks like a subtract. If we actually look at how that's implemented, so here's operator minus. On two F32s, it's going to issue a sub PS just like you would expect. But if you look at the v3 version, right, it's going to do that on several of these. So it's going to be 3 of those sub PSs. So each one of these lines here is 3 instructions long, right? So that's going to be 3 instructions. That's going to be 3 instructions, right? 3 instructions, another 3 instructions, right? So the number of instructions here is actually pretty high, right? And it's not like we can't afford to do some instructions or anything. Obviously, in lighting, there's going to be several instructions. How do I actually get to, what am I looking for here? Lighting, there we go. Oh, and I can do a Control F now, can't I? So I can actually jump right here if I want to. Look at that. All right. So inside this code, right, if we actually look at what has to happen, if I go ahead and set a breakpoint here, and we go ahead and look at the disassembly, which is what I actually want. Looks like that window's not open. There it is. So if we take a look at the disassembly here, what you can see is, there's a lot of code that's going on here. There's shuff PSs that are, there to sort of distribute things out, like this sort of thing right here, right? Lofts this single value up to replicated stuff. So there's shuff PSs for that. Then there's the sub PSs that are happening, right? Shuffs, subs, there's mobs that are moving in the data, right? I don't know why this is storing this out. Some stuff there that doesn't make a whole lot of sense, but it doesn't matter. Point being, you can see mul, max, min, shuff, right? There's tons of code happening in here. And to some extent, we can start to minimize this because on certain things, like for example, the boxes, we know we can control how those boxes are created. So we could, for example, just pre-store them with some of these things computed. And that's definitely something we're going to want to do, right? But the point is it's fairly expensive. If we look down here, right, and we look at what's going on here, you can see that we do this box intersection test, but the only thing we're ever going to do when we intersect the box is we're just going to determine whether we should go and look at the children of the box, right? That's it. And so that's just not a particularly useful way to construct this tree. Instead, what we could do is, because we've basically constructed it, for example, like a KD tree, this is way more expensive than it needs to be. If you look at what we're doing in our split box, right, here's where we construct the bounding volume hierarchy. We're basically doing a KD tree here, but there's no reason for it to ever, like, it doesn't actually ever use that knowledge in here. Right? It does a bounding box check, even though the only thing is it's just a split plane, right? This is basically a BSP, but instead of testing it like a BSP, we're testing it like an AABB hierarchy. Right? We're just throwing cycles away. So this piece of code, it sucks, right? This is not smart at all. And we don't really know that we can save time by improving it because we don't really know to what extent we are, we don't know exactly what we're limited by. We don't know if we're limited by cache concerns. We don't know if we're limited by branch mispredictions. We don't know if we're limited by math ops, right? We just fundamentally don't know. And if we wanted to know for sure, we should probably take some actual measurements, right? And that may be something that we want to do, meaning we'd pull this code out, we'd run it in a more controlled setting, and we look at what's going to happen there. But at least as far as we can tell here, there's no reason to believe we wouldn't get a win on basically all of those fronts by just not using AABs for this. If we're going to use a KD tree anyway, which is how we did the splits here, and generally speaking, KD trees are what people use for ray tracing most of the time, we could reduce all of this just by using a different type there, right? So if we actually look, and plus, let's take a look at getbox, right? So, getbox, for even this, we don't need to call, right? This is just doing a straight ahead lookup. So, you know what? And this is even worse. This is a double indirection, right? For no reason. Although that may make sense up here because we're trying to use the existing set of boxes that we got handed so that we don't copy them the initial time. Even that's a little questionable. We should probably just flatten that down. Even if we weren't going to do that, looking here, there's no reason for this because we created these boxes that are the sub boxes in the set. They should just be continuous in memory. So before we get too far down the road of trying to actually collect information about this, I feel like we probably would want to just fix all that, right? But it may also be instructive, I don't know, to sort of say, look, well, maybe we should create the test harness for that first, right? So I don't know. I'm going to go ahead and say maybe I'll look at how much work it will be for me to isolate this piece of code out and then look at its performance separately. I want to say that I installed vTune already on this machine. Let me see if that's the case. Looks like it, right? Because I believe we were using this one time I did a Meowhash stream. I don't remember if you folks who watch the stream regularly remember that. But we were using, to be honest, I don't actually know that there's a way to do command line performance analysis on Windows. On Linux, there's an executable you can call called perf that allows you to actually get your performance counters without having to go through a ridiculous tool like vTune, which I don't super love. But on Windows, the only way to get access to like the more sort of specific performance counters that you're going to get, those only really come through vTune. So if we wanted to take a profile of this particular application, we really kind of need to know what's going on vTune-wise there. And so what we could do is break this out into a piece of code that we can then look at and be a little bit more specific about. And that might be worth it because then we can take some actual timing, pieces of timing information that are more specific and get a little bit more information about what's going on, right? Now, in order to do that, we kind of need some way of actually getting information out of our system. We need a way to sort of do this procedure offline. Thankfully, the lighting system really just works on sort of these box inputs. And so here's what I'm going to say. I'm going to actually say, let's just let it take a capture, okay? And we'll just let it write to a file. If we look at our Handmade platform code, I want to say we actually have the facilities already built for this. So let's just capture some of the data, use that. You can see we got platform write data to file here, right? So we should be able to actually just open a file, blast some data out to it, and then use that in an external test app. So it's nice because again, I don't want to go down the rat hole of why you should always program simply and why I don't even bother arguing with people about this anymore because I feel like the shark has been jumped. So, you get these modern C++ people and they're just off in la la land or whatever, right? But again, when you just program sensibly and you just have like a basic array of some data, stuff like this is just a non-issue, right? If I want to capture the input to one of my things, I could just write out the array, right? It's not some giant rat's nest of ridiculous RAI classes that all point to each other that have to be crawled and just like, who the hell knows? And then there's like, all serialization and, do I use a library? It's all just a waste of time, right? It's all just a waste of time. Because begin lighting computation, we go through here, we get this input that's just like, look, this is what you're going to do. Our split box call, like when we call build spatial partition for lighting, that just comes in a very simple array, right? You can see this is all we do, right? We just loop over the boxes we got as an input and then we build it. We can just write that out as one flat piece of data and be off to the races, right? So again, really, really simple. And the reason for that is we just weren't dumb, right? All we did was we didn't overcomplicate our lives with a bunch of nonsense that doesn't have any practical benefit, right? So what I can do here is inside build spatial partition for lighting, if I want to, I could go ahead and use the platform IO stuff to just say, why don't you just write out that flat array? I'll load that flat array back into my program in just a standalone exterior program, and then we can actually run the lighting on an actual scene so we're not making stuff up and taking timings on something that isn't really appropriate. So if I want to do that, what I should be able to do here is just go ahead and say, look, if I call the platform API, so I'm doing, something like this, I should be able to do like an open file, and then I should be able to do like a write data to file, and then I should be able to close it, right, like this, just closey. And then I can, dump out this thing that I was using, the solution boxes here. And then I can just do the same code that I was doing before, and in theory that will give me everything I need, right? So let's go ahead and try to do that. If we look at the API for that open file, right? If I, trying to actually get a platform open file there, I think I should be able to do that with this. Is this only for iteration? I don't know if this there is a way to create files. I just don't remember exactly what it is. I think it's this platform get file by path. So I think maybe that's actually what I want there. Platform get file by path. And then what I have to do is I have to pass it like some information. And I don't know if that's the right way to do it because it's been so long since I've done any of this stuff. And this is made for our asset system. So I'm not 100% sure that's the smartest way to do it, but I think that it is. So if I go ahead and do it this way, what are all the things I need to use there? A platform file group, which is just this. I don't remember. I'm going to go look at the 132 code. So in here where we have like Win32 get file by path, I think that's really what we want because I think it works pretty much. Yeah, I think it works with whatever we want. So we can pass, we don't have to open a file that exists. You can see here that like if we specify open file right, it will create the new file for us, right? So that seems like what we want as far as I can tell. Win32 open file, we should be able to then just pass that file info that we got back and off we go. So I think we're okay. That's my argument. That's what I'm going to claim. So here, if we look at what happens when we actually call that get file by path, that gives us I don't know, we'll call this the dump file or something. I don't know what we're going to call this. This is where we're going to dump our data to. We should be able to open that file. And oops, I think, is get file by path modified? No, that's fine. All right. So open file, I think all that open file needs is to know open file right, looks like. And then the file group. That's the only thing we don't have. So there's the file group. I think they get passed to everything, does it? So here. And then when we do write data to file, we just pass the handle we got back, right? So it looks like that. And the offset, the size, which we'll have to compute, and the source, which is just the boxes, right? And then I guess we close it. I don't know that we need anything there. So I think this is literally all we would have to do, but it looks like we'd have to open a file group for that, like this. And so if I just said okay, platform open file group, and then platform close file group, I think that's everything. And if we were gonna do this a lot, that's too much work, right? We shouldn't have to do that much. So there probably should just be a debug dump file kind of a thing, somewhere that we would have, and we don't have that at the moment. Yeah. You can see we don't have any of that, as far as I can tell. So, we should probably wrap this up in a dump thing. It should probably be something like this that we can use anywhere we want. Something like that. So that way, if you want to do just debug dump data, something like that, you can basically just say, give us, I don't know, a name for the data that you actually want, right? Data name or whatever. And then it will do this work for you. You just give it how big, was that supposed to be? and what was the data you actually wanted to dump, and off it would go. Something like that. You know what I mean? So I think that's all we really need. And we can also then use this in other places. So it would take less time next time to do the dump, because we, would have a purpose-built API that opens and closes the stuff for us. So what I'd like to do there as well is, I'd like to then say we've got a platform file type for dumps, right? Because basically, that's the thing that's gonna, we'd want to have a directory where those go or something. So exactly what this was previously used for, we would want that to happen here as well. So in here, I would say, we've got our Handmade hero directory, and we've got a debug directory that stores this stuff. So actually, I would say that's probably where that should go, right? So inside the debug directory, we should be able to open that up for dumping, dump files there, and again, this will do, I think, roughly what we want it to do, right? Oops, that should be .dump or something, right? So when we do get file by path, I don't know if it automatically adds the dump prefix in there. It seems like it probably wouldn't. I don't actually know though. So again, I'm just gonna, it's been so long since I've looked at any of that code. I'm just gonna take a look to see whether the, the get file by path stuff actually appends anything. I don't think it does. Yeah, so it doesn't. So I think what I should be able to do is in here, maybe say file name. Again, it's a little weird. Does this use... I'm not sure how this figures out where stuff goes, because it feels like this should actually create a path that... It just feels a little bit buggy. Like who puts this path together so that it's in the right place? This file name here, I feel like what I'd have to, I think, what I'd have to do here is say something like debug / lightbox.dump. And then I just say, oh yeah, the size of that is size of solution boxes, times however many those were. So, this thing right here. And that would do the whole dump, but I feel like I shouldn't have to do that. It would be nice if you just did that. And then when you did an open file with the path in there, it would say, well, whichever file group that was under, it appends it, right? So I kind of think that, shouldn't I be able to not use debug / here? I don't know. It's not a super well thought out API, the file stuff. It's just for the asset processing, so it's not something we really know is particularly great. So I'm not super concerned about it either way, but I just wanted to drop a note there because I'm like, that seems a little bit squinky to me, so, maybe not. Anyway, so I think we have a global platform handle for that. In handmade.h, I want to say, or something like that, we've got one that we actually just store it because that's accessible. It's an API that's accessible to everybody. You don't need a particular thing for it. You can see that it's right here. So I guess what I'd say is maybe let's just put that in here and make people call through it, which seems good to me actually as well. So in here, we would just say, okay, I guess I don't know. I don't know if that's externed anywhere. I guess it sort of is. So I guess I can really put this anywhere, right? Yeah, I can. So I can put this anywhere. So I think maybe I'll just put this in here, right? And I'll just export that as like a function that people can call like this. And, you know, we'll leave it at that. So now anyone can dump data out to our dumps directory. I don't know what that open file group call was actually called. Let's look at it here. I guess it's this, get all files of type begin. Get all files of type end. And we now know we've got a type of this, which is the platform dump. And there we go. All right. So get file by path wants another parameter. Not sure what that is. So let me just look at the actual, let me look at the actual call for that. So that's get file by path. It needs file group. Oh, and we need the path. We didn't pass it. And that's an address of, I think that's it. So I think that's what we want. And I think that should dump the data. And if I run the program now, well, actually, I guess I don't remember if I actually put in here an actual call. I did. If I run this now, I think that should just constantly be dumping the data to it, right? And so, yeah. If we want raw dumps, I think that's all we really needed to do. And that gives us the complete set. So what I need is just some way of actually triggering this. I don't actually probably care much about it, so maybe I'll just do that. And then I'll just change that to a 1 if I want to make it go, right? So, and you know, the other way I could do that here is I could say something like, okay, you know, maybe we've got a global, you know, light box dump trigger, right? And then we could do this. And that way, if we just set light box dump trigger to true, it will dump the data. So that would allow me to like walk to, I don't need this breakpoint anymore. That would allow me to walk to where I want to be in the world. So maybe I want to be in some place that's like, you know, got lots of stuff in it or whatever. I mean, I don't really know what the best place to be is for it. Maybe I want to be like out where there's more like layers to the thing. Like out here, you know, where we start paging in more world stuff from like dungeons and stuff, right? Like that's a lot of boxes, right, in the system, I would think. So, you know, if we wanted to, we could say, all right, let's go ahead and take a debug dump in that location. So I guess all I really have to do is look for that variable and set a breakpoint. So if I set the breakpoint here, and then I don't know, can I set this variable to something? I don't know if I actually can. Where is this thing? I'm not sure. Is there editing values in Remedy? I don't actually know. That's a good question. That would be a good feature to add to the list. I don't think I've ever actually tried it, so I'm not sure. At this location, memory. That was cool. I like that send memory to watch window. Am I allowed to change this? No, I'm not. All right, so I have my first feature request for 3.0 branch. Can I edit that? That's my request. All right, so if I want to change this, then I guess I'll just do it this way because I don't really need to do it the way I was doing it. I guess I will just go to here and say true. And then in theory, like I should watch this, it should stop. on that line now. And if I go in here, I should like open something. I mean, I don't really need to walk through this, whatever. It's going to do what it's going to do. And then in theory, I should now have, if I kill the program, I should now have a dump of that if it actually worked, right? So if I look at the debug data, there's a lightboxes.dump. Hopefully it actually has the data that I actually want in there, but that's like what we would need to read in an external program. So if I want to, what I should be able to do is actually create sort of a standalone thing that's going to load this and then use the lighting system separately. So if you take a look at we've done this several times before, like H8 sphere, for example, in the build.bat, we have there's a sphere builder, right, that we use for our lighting. And if we look at that, it's right here. We could just make another one of these, which is like lighting profiler. I don't know. And all that would do is we'd build HH like light perf or something, right? Or HH light prof. And that would allow us to create some other executable that is there solely for the purpose of profiling the lighting system, and it doesn't do anything else, right? So we do HH light prof.cpp here. We open that up. We basically copy this exact piece of code that we had before, and so that we can build Handmade Hero-y looking things with Handmade Hero actual code, rather than all of this nonsense about the spheres. All we would actually do is stuff in here. Excuse me, I've got something in my eye. We would just say, all right, when we run this thing, we'll grab an argument that is the lightbox dump name or something like that, right? We don't care about any of this at all. We're gonna RB this thing, like RBs, like roast beef. We're gonna open up the lightbox file. We'll read the entire file here. If we can't, we'll just let people know. And that'll be that. Right? So this is all we really need to do here, and we'll just use this as our way of debugging the program. I don't know if I can include the lighting here, so let me just go ahead and do a test build first and see if we can make sure that this works like so. There we go. Oop. I don't know what that's about. Is that a bug? All right. Anyway, so I want to be able to do this. Like, I want to have the ability to call our lighting functions. I don't know if we can actually do that. You can see that there's some stuff that's missing in this case. So lighting box is actually in, it's in the renderer code, right? And we also need the H file. So world position, I think that's just in here. That's not how you spell that. Yeah, and debug dump data can just be stubbed. And I think that's all we really need there. That's going to have to go up above the actual lighting code because it needs to be able to find it. What else we got? Set light bounds, enable lighting, dev mode lighting, global lighting show probes. So some of these... push line segment. Some of those are just in the renderer code. I don't think we want to do that, but we could. Dev mode lighting. I don't know what that actually is. I think it's in the editor. Somewhere. Not actually sure. But here's what I'm gonna actually do. All right. So some of these we actually have to bring in probably. I'm just guessing. Are in same chunk, for example, is a bit of an issue. Maybe I'll just grab that. Are in the same chunk because it's not important here. So I'll just say like and again, this is just me compiling a separate executable sort of out in the out in the wild here. There's another way I could do this, and we'll see if I have to do too many of these, I'll do it the other way, but for now, I'm just going to do this. And basically stub these out because I don't care about them, right? All right, so now, at least in theory, I can go and, if I want to, in the debug directory, I should be able to do something like lightperf lightboxes.dump. Like prof, sorry. There we go. I should be able to do it. That wasn't happy. What happened there? That's what happened there. So I should now be able to debug this program as like a separate program. If I want to, I should be able to create a remedy debug profile for it as well. So hopefully I can just, go ahead and, oh, you know what? This is something we meant to fix as well. Let's fix this because I feel like I forgot to do that many times here. So in our misc directory, we have our remedy batch file. This is like not supposed to happen this way, right? The start needs to get removed, I think. So let me just see if that fixes that. Wait, but we still need, but we still need to call that start call. What am I doing wrong here? Do you have to do that? Maybe? Nope. So I thought there was some way, maybe X13 can tell us. I thought there was some way to like get Remedy to use the things that I just passed to it as the, ooh, I like that. As the, as a startup stuff here. But I don't know if that's true. It doesn't really matter to me, but I figured I should probably fix it at some point. Might have to append exe, but I thought that worked. Oh, okay. So apparently... Oh, yeah, it does work. So I guess you need to actually say exe because it probably just couldn't find it. So never mind. I didn't need... It looks like I actually did fix my batch file, so that's good. I thought my batch file was broken, but it's not. Never mind. All right. So yeah, so I can now create a debug profile for this, and I'm just going to save that off so that we have it. HH light prof. So that way we can quickly like run the thing and debug it and whatever, right? So here we are in here, and you know, we did some stuff and whatever. No one cares. Anyway. So now if I want to do this, I should be able to say like, look, splitbox is a thing, right? And I should be able to actually call exactly what we're doing, so I can build a spatial partition, and then I can test the spatial partition and all that good stuff, right? So I should be able to basically run exactly what I am running here almost verbatim, right? Like I should be able to say, all right, like let's go ahead and run the spatial part, you know, let's build the spatial partition for lighting using an actual lighting solution, right? So I should be able to do something like this, where I say like build a spatial partition for the lighting, and I'll have to obviously, and in fact, I suppose I could do that here. So if I pass a lighting solution to this, I should be able to then call build spatial partition for lighting to build the spatial partition that we actually have. I should then be able to also like effectively just do the work distribution. So I should be able to say, look, if I create a bunch of these work units, I should then be able to actually call the raycaster, right, if I wanted to. Now, I don't know that I actually want that per se. What I might want to do instead is say, all right, at the moment, you know, maybe we want to do that eventually. At the moment, I may just literally only want to test the raycaster like in a loop, right? So I may instead want to say, look, I just want to call this thing, right? So I want to call this thing here. So maybe I'm just actually going to create a lighting work structure. And then I'm going to call raycast on that lighting work structure with, you know, all of this garbage. Right? So if I wanted to do a raycast this way, I could just test this manually and not actually do the work distribution. And I think I might want to do that because I want to be a little bit more specific about what I'm testing. Like right now, I don't want to look at like the diffuse texture builds and stuff like that. So if I actually went through the whole work distribution pass, it would do a bunch of other stuff. And I want to kind of just look at the raycasting. So kind of my goal here is to get a little side program working that only is going to cast rays. That's all it does. And then we can profile just that, you know, just that particular thing, you know. So if I'm going to do that, I need a couple things. I need the spec and diffuse atlases, and I need the spec texel, right? So if you look at what's going to happen in here and we take a look at what's going on, we can sort of go through the lighting solution and see everywhere it's actually used. So, you know, there's like the root box index. That should get filled out. There's a t-update blend we're going to need, right? So up here, we should start setting those things like the t-update blend. And we don't really care what that is. As long as it's not a weird singular value, we should be able to set it to anything we want. Since there's a constant in here that I think we can just set it to the exact same thing. It's like 8/60 or something. I don't actually remember what it's set to, but we should be able to basically say, look, it's just this. So, you know, we'll do the same thing. Might as well. No reason not to. So if we take a look at what's actually in the lighting solution up here, and we take a look at what all these things are, we're going to want to actually set like most of them to be the correct proxies of things we actually would need for anything that actually matters. So like the voxel will have to get set up. The rest of the things, probably not so much. The diffuse weight map should probably get set up. Well, actually, no, we're never going to look at that. So the sampling spheres should probably get set up. That's about the only thing, I guess, that we would need there. So let's make sure the sampling spheres are up there. And then we need to set like all of this stuff up, right? And that's going to come from the file that we actually saved. So this stuff should get set up in the file, from the file, like here. So we're going to set the box count. And this is where we'd actually get, you know, we're gonna need like a malloc here, right, to get a malloc and an fread to get from the file the stuff that actually goes in the actual boxes, right? And so we're gonna need to load that up, and that's totally fine. We also need a couple other things here, probably, I would guess. Do we really? No, maybe we don't really need much else. That may be mostly it. So I think the only thing we really need beyond there, like I said, is the lighting spheres. We need, obviously, but we can just get them from the include file. So the lighting spheres, and then just the voxel information. And I think that's most of it. So let's go ahead and set that. So there's the T-update blend. Here's the random series. There's the sampling spheres. We don't need the work distribution array. It's not necessary. The voxel dim and the in-voxel dim, we probably do want, right? And hopefully we can work that out. Fundamental unit, we may not have, I'm not sure, right? Let me go ahead and if this out for one quick second. Actually, and this as well. So fundamental unit is something that gets passed in, probably. Yeah. So I don't know that we care about the fundamental unit at all. Probably won't matter other than to profile our voxel lookups. So when we call in it lighting, I suppose we should probably double check. And okay, so it's 1.4 is what we were setting. So, you know, sure. It doesn't, I don't think that actually matters like at all what we set that to for the most part. But, you know, just to make sure we're profiling as close as possible, we'll keep the same constants. But, you know, I don't know that that's going to make a particularly big difference either way. All right, so I think that's mostly what we need to make all this stuff work. So now we're really talking mostly about Spec Atlas, Diffuse Atlas. I don't know where those are going to be coming from here, and so we're probably just going to have to set up fake versions, and we're going to probably need to actually allocate the memory for those just to make sure that, because, you know, this code writes into that, so we kind of need to have that backing buffer there. So, you know, this we can nerf temporarily just to get it compiling, but then we're going to want to actually generate arrays. The Spec Atlas and Diffuse Atlas, those are going to have to get passed in here, like so. So we need those. And we can just we can init those by doing a make light atlas call. So that shouldn't be a huge deal. And then we can just do a test raycast call, and this should, you know, run the raycaster, right? So I think that's the setup we're looking for. Oops. And I don't know that we need to actually go so far as to pass an actual spec texel, at least for the kind of testing that we're doing right now. It doesn't seem particularly necessary. So what we should be able to do is a get texel call on it more directly. So when this thing actually, like if we look at the way the lighting code was doing that, when it's actually doing the distribution on those texels, in the work callback, which is right here, when it gets a texel, it does it like this, right? So we should be able to actually just do that, right? We should be able to say, look, just get it. I don't care which one. We're not profiling the rights to the texel at this particular time. So just give me something, and we'll pass that down, and that, you know, that's what you'll use. So hopefully that gets us to the point, Hopefully that gets us to the point where we're really just focusing on loading up this initial data. When we look at those light atlas calls, again, I can, if I want to, and you know, I might as well. just go ahead and take where we were doing the light atlas generator, which probably this, right? What I can do is say, look, let's just do this. So here's the thing that, oh, nah, that was not what I wanted at all. Why did I paste that in there? All right. I meant to paste it in here. So let's just do this. We'll actually use the constants. We can tweak these if we want to, but again, I don't think we care. So we should then be able to say, all right, here's the diffuse atlas. Here's the spec atlas. And now they're initialized with the actual settings that they should, in theory, have. Right? And then we would want to, I think, and give them some backing memory, because otherwise it'll write into nowhere. So we probably do want to do a thing where we at least do call this. So we probably do want to set the diffuse atlas texels to some malloc thing, right? So what we want to do here is get the entire set we might actually need, and I think you can just do that with a call that's like, give me the size. I think it's this. So all that's doing is saying, look, just allocate however much memory this thing says it needs and give it to it. So that creates a fake environment that's similar to the one that runs in the game without too much trouble. All we need now is those actual boxes. So what we want to do here is, get a file size. So we'd want to do something like this. For some reason, C runtime library. Never thought the size of a file would be something you'd want to know. Yeah. So if we go ahead and do an fseek on this and just do like a seek set. Seek set seek end and do an ftell on it. That should give us the file size. And then we can malloc the file size, right? And fread it. I don't know the box count in any particular way, but I can get it pretty easily just by saying whatever the file size is, that's how many boxes there were. Right? And it looks like this has to be 16-bit because we don't allow bigger than that. Right? And that's it. That's our test app. I think that will literally do the whole thing, right? Now, I don't actually want the global debug table. So I think what I'll do here is turn that off. So in here, I'll probably do like a pound define, like handmade, like undef, handmade, internal. So the debug code is gone. I'll also turn off handmade slow. So basically, like, the certs are gone, the internal code, the debug code's gone. And off we go. So I think that should recreate our test scenario. I don't know why this is still here. Shouldn't be. And now I think we can save this highlight prof up. So now I think if we just load remedy, it should just be in our drop-down list. We can select the light prof and run it. Right? So I think we're all good. I think that's all we substantially needed. And we should be in good shape. This, I don't know if there's a size issue there. So if we look at the lighting solution here, I don't know if that's too big. I'm going to move it out. for the stack. I think it probably is. Yeah. So there you go. We're running our test program. Everyone's happy. That actually, in theory, does an actual raycast, I think. So if we come through here, I mean, in theory, this is a release build. You know what? Let's actually step through it. Let's just do it. So that's going to be in work directory, handmade, debug, right? Step in, open the dump file. How many boxes are there? Oops. Not the best spelling in the world. 0. What? Did I flip? I did. If I had $1 for every time I did that, typed enums, it'd be nice. All right. Anyway, let's go ahead and try that one more time. I'm like, it ain't 2 boxes, fellas. Much better. Much better. So, in theory, if we read in these boxes now, like I should be able to sort of like look at them and see that there's actually some data in there that maybe is theoretically plausible, right? So like, you know, those are good floats, right? So, you know, looks sane. It's kind of what I wanted. And if I looked at more of them, so I could do like solution boxes. I think I can just like say I want more of them, right? And then, you know, still looks good. So it, you know, that looks reasonable. If the box count is 343, then maybe I want to look at box 342, which is the last box, just to make sure that it doesn't get weird at the end. It doesn't appear to, so that seems fine. So off we go. So, all right, that all looks fine. Now we have the problem. I think this should crash immediately, though, because it doesn't have room to create boxes, right? Shouldn't it, in theory? Yeah. So we need to pad out that box array, and I don't actually remember much about how that gets done. So I'm just going to do it in a sort of, you know, arbitrary way. Look, you know, don't use 4 times more boxes than you get inputted, right? Which should be impossible because since it's doing a binary split tree, basically, in theory, you know, you shouldn't have more than log n boxes added to the box set, right? Or something like that, you know, order log n. It doesn't matter. Point being, I just want to give it some headroom. And then I think we can run it. So that looks like it's having trouble with a box. Which I don't know why it would. Here's the solution. These are fine, obviously. So what's it having trouble with? Box. The box it got must be a not real box. Yeah. So what's the box index? So that does seem strange because we just saw the box index set to something. Oh! Yeah. We want to allocate this many, but we don't want to tell it there's that many. So what we actually want to do here is just allocate more boxes, right? So just give it some overhead, right? Some extra space at the end to use. which we're going to undo that in a minute anyway, but, you know, off we go. So let's see what's going on here. So one more thing we got to do, it looks like, is we got to fill out that work order. So I forgot to do that. Let's fill out that work order. So in the work order, I don't know that we can fill it. We can't fill in the commands really. So we'll fill out the solution. Voxel X can, I think all the rest of the stuff can still be 0. So I think that's fine. Oops. And now we're all good. So now we're running the test, and we're running the test pretty reasonably, right? So we created a fake environment. We then actually we do raycasting. And so now all we really need at this point, I think, is to actually put in the sampling sphere randomness. So instead of calling raycast, like these are 2 garbage values, right? Like that's not sensible, right? So I think what we need to do now is actually make some way of calling this with some real code. So if we look in here at where the lighting is actually doing that call, you can see us getting the sampling sphere out of here. Let's go ahead and do that, right? So this sampling sphere pull, and then the pull out of the sampling sphere, I'm gonna copy that into the light perf. It'll look something like this, right? And that's how we'll get the ray origin and the ray D. Now, the origin, I don't care what the origin is particularly much. It would be nice if we were using an origin that's like similar to something that would be used in the game. 0, 0, 0 isn't ridiculous, so maybe that is just what we'll use. But ray direction needs to actually be set. So we'll say that ray origin's still that. We'll then say, all right, let's make a for I loop here. Around the raycasting where we're going to do it like over and over and over and over and over and over, right? So we'll say like dir sample index equals 0. Dir sample index is less than, some really large number of things we're doing here. So we're going to raycast and raycast and raycast and raycast, and then we're going to raycast some more. We'll go ahead and say, oops, this should be empty index, sorry. We'll then figure out which sampling sphere we're trying to actually sample here, as you can see, and then we'll pull out, the ray bundle index off of that, right? Now, the ray bundle index, I don't know where that actually gets set. It looks like, so that's a separate loop inside of here that loops over the total number of ray bundles that there actually are. And so we should probably mimic that behavior, right, to a certain extent. So we should probably say that we do it like this. And the ray bundle, like that, like index thing, we'll just go over every single one, because that's sort of what would be happening in the actual app, right? So we then pull out the sampling sphere for whatever directional sample we're looking at, and I guess we could do that here. And then we pull out the ray bundles for each particular bundle. Yeah? That seems reasonable. And so now if I run it, it should sit there for a while, do a bunch of raycasts, and exit. And we're probably going to have to like lean on it really hard to make sure that it just does a crap ton of raycasts, like raycast, 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 raycast. And the reason for that, if we want to analyze the profile of this and we want to look at how expensive it is to do these raycasts, we're going to want to look at a representative slice in the middle. And as you'll see, when I go to use VTune, the sort of bloated, bilious VTune, I'm going to need a way of not having it time a bunch of random crap. And so a bunch of that random crap is stuff like, how long did it take you to load the file, right? The dump file. I don't want it to count any of that stuff, because if you're getting a bunch of cache misses and when you go into the kernel to load a file, well, that's not going to give me any information. So what I want to do is I want to make sure the program that I run, and there's different ways to do this. You can actually like include a DLL in in your building where include DLLs wrong. You can load a DLL and use, do a get proc address to vtune to say, here's where to start the profiling, here's where to stop. But a much easier way to do it that doesn't involve any, poisoning the code in that way is to just actually make sure your application does a crap ton of the thing and then just tell vtune to start profiling 10 seconds in or 5 seconds in, right? Because at that point, you know that all of the cache stuff and all of the kernel transitions for loading files, all that crap already happened, right? That already happened, and you don't need to worry about it. It's not going to get counted in the profile, and it's just going to jump on in and start profiling the part that's the actual meat of the algorithm that we care about. So that's what I want to happen here. And so, this piece of code would just do that, right? So what I want to do is make sure that I have enough of these. Let's say that we're just going to keep on doing this until, a heat death of the universe and all that. And so I run it and, it stays up for a good long time, raycasting and doing its thing, raycasting. And then eventually it will actually exit. That's maybe too much. Let's back off a little. Still maybe longer than I need. Seems pretty good, although I might even drop it down a little bit more. So I didn't really need to spam it much. It was pretty good. All right. So now we have a single-threaded standalone app. If we literally just want to look at sort of the fake theoretical behavior of our routine, we now can do that because we have an isolated fake case that shows us theoretically what's going on. Now, it's not an exact replica, and we don't actually want it to be because the exact replica is the thing that runs in the game. And what we're wanting to do now is take away some of that variability and just look at, theoretically, if we're just trying to push this crap through the processor the way that we were on a single thread, so we don't have multiple threads contending, not two hyper threads, none of those things. Can you just tell us sort of what's going on in our code so we can start to tweak it and just see what the result is behaviorally? That's what we're trying to do here. And you'll have to forgive me for I am not good at vtune. I normally just use a Linux machine and run perf, which I find much easier to use. The vtune kind of weirds me out, and it's got all this weird trappings that just, I don't know. I don't understand why it has to be so complicated. I just want Intel out there. If you're listening, you're not, but let's say you were. I just want something where I can just do this in my code. I don't want any of this. I wish I could just, I don't know. It doesn't matter. Point being, inside vtune, this is what it looks like. They made it free, and thank you Intel for doing that. They used to charge an exorbitant amount of money for vtune, so nobody used it. But they eventually made it free for if you don't, there's some part of it that you don't get. I don't even know. It doesn't matter. The point is, it's free now, and you can just install it on your machine. You just make an account, you can install it, and that's good. And so if you want to, I can create, like I'm doing here, a new project. I could create a vtune project that I can store, and I'll do it in this work temp directory because I don't know if I don't really want to pollute all my stuff. But we'll basically say all right, let's call this HH Lightprof, create project. And what I should be able to do now is, just tell it, I want you to take a look at this application and start to tell me stuff about it that are based on profiling counters that are in the CPU, right? So normally, I just want to access that stuff. And you see me do that in Handmade here before. Our entire profiler is built on the fact that we could just call RDTSC, which is read timestamp counter, which basically says, get me this particular performance counter that's inside the Intel CPU that just basically tells me how many roughly clock ticks went by at any particular time. Great. There's a whole other set of performance profiling counters in there. And when I say there's a whole other set, I mean, like, you have no idea. If you've never done this kind of profiling before, so you've never looked at the perf counters on a modern x64 processor, you are in for a treat/headache because, oh my God, you have no idea how many things you can profile in a modern x64 CPU. There are so many that I'm willing to bet that there's almost nobody on planet Earth who actually knows what they all are. I'm just going to say that there's probably very few people. I've actually done passes where I profile every perf counter that I know of. It's like in the hundreds, and I only know what some of them actually measure. Like, there are probably, I don't remember how many there are. I actually did know exactly how many there were that I could find documentation for. I want to say that out of those, there were probably 10, maybe 20 that I literally just have no idea what they actually count. I just don't know. A lot of them you can tell by reading. It's like, oh, this counts anytime, like, you know, the CPU missed the L2 cache and this happened or whatever, right? But some of them I like read and I don't even know what this counts. There are so many of them. So anyway, with that out of the way, we're just going to be doing some basic work with this. We're not going to try to do anything that fancy at all. So we're going to go to HH Lightprof here. We're going to pass in that light dump, I just want exactly this, right? I want to run exactly what we're running. So I want to run that, and I want the working directory to be the same working directory. So we know that it will work, right? We don't need to set anything else up in here because nothing particular is happening. The only thing we need is this bit here that I was saying. We want to... oh, that's not it. Where is it? Here it is. Here it is. Okay, sorry. Automatically resume collection after sec and automatically stop collection after sec. That's what we want to actually look at here. So what I want to be able to do is say, all right, I want you to basically start the app, and for like 2 or 3 seconds, let's say, maybe 5 seconds, or something like that, right? Don't take any profiling. So I think that's all I probably have to do. I like I said, I haven't used this in a while, and it's hard for me to remember sometimes exactly what I have to do. But I think that should do it, right? So anyway, that's what we need here to have a way to launch the application. And then what we want to do up here is, you can see like I want hardware event-based sampling. That's just saying it's going to take a look at what's going on in the hardware to count the counters that I ask it for, right? And I don't remember... Analysis type. Okay, wait. The duration time estimate option is deprecated. Use the CPU sampling interval option on the analysis type configuration pane. Okay, so you're telling me don't set this? Wait, but... I don't understand. I can't not set this. Okay. I don't know what to make of that, but okay. So in analysis type, which I think is in here. Yeah, okay. So what we want to do here, you know, and there's a couple different things we can do. Obviously, we can start checking the hotspots just to see what it thinks are the performance bottlenecks, which is also good. But microarchitecture exploration is what I want to probably do eventually, and that's just the thing that lets me look at the actual code and see what we think is going on there. Let's just see what happens here. Like I said, am really bad at using vtune, so we'll see. I'm going to go ahead and start it. Let's see if it works. It should unpause the collection automatically. It does. And there we go, right? So hopefully now I will get some actual information here. What you can see in terms of what it's telling me about what it saw, the I don't think we've ever talked about a lot of this stuff on Handmade Heroes, so I'm not sure where to start. There's a couple different things that we now need to start looking at to start to make this code run high performance, right? So there's two separate things. One thing is making sure that the code itself is doing the smartest set of operations that it can do, right? This tool will not tell us anything about that. So the thing that I was talking about before that we're going to want to look at possibly even first, and so I just wanted to get a run of it with the existing code, which is why we're looking at this. I don't necessarily need this information right away. But so we have to go think about whether we're actually doing the ops we should be doing in the first place and stuff like that. This tool can't tell us anything about that, right? The second part is saying for the ops that we're actually doing, right? Like when we actually decide we need to do this stuff, how close have we gotten to actually utilizing the chip with those ops, right? And sometimes we may be in a situation where like there's really not much we can do. So we look at the code and we're like, well, we have to do this stuff. There's no way we can really utilize the chip very well with this stuff, so that we're out of luck, right? But other times we can look and go, oh, okay, I see, using a tool like this, we can say, I see why we're underutilizing the CPU, and there's ways we can fix that, right? So, looking at this, you can maybe start to make some generalizations. It doesn't matter right now because we're not even in a release mode build, right? So this, we don't really care about, right? So let's start by just saying, all right, let's run a build. I think I can just run a build, right? Let's just run a build that's with optimizations on. So this should be some reasonable code in theory. Let's see what the hotspot analysis looks like, just to make sure we're actually getting that. Although actually, so the problem is that's now running so fast, we're gonna have to add more delay to it. So let me go ahead and just up that. That's still not long enough. All right, so my estimate before was actually accurate. It's just I forgot we were in a debug build. So that's better. So now I'm going to go ahead and say, all right, let's go ahead and rerun this. I think I can just do this. Again, in the orgy of windows in here, I don't even know. But anyway, there's there's the sort of information that we got. This is not a diagram we can use because this is talking about multi-threading. If we want to go profile the work completion and we start multiple threads or something, then we can start looking at this. But this doesn't really tell us anything because this is just looking at core utilization, and we know we're only looking at a single thread right now. So this is actually the number that we care about right here, right? The microarchitectural usage. And if we look at that, we can kind of see that it's actually pretty high. 80% of pipeline slots filled is not terrible, right? So, it looks like the code itself, right, at this point is not super bad. I forget how you get all the stuff you actually want here. So, if we look at what the code looks like, let me see if I can... and I'm not sure. I thought you could see. No. I thought you could see more than that. Maybe it's this? No. There we are. Yeah. Okay. So, if we take a look at the code in terms of hotspot analysis, so this is kind of, it's not really very good necessarily, so you don't want to put like too much faith in it. But if you take a look at the raycast routine, this on the side, the CPU time like list here on the side is sort of maybe kind of a little bit possibly sometimes trying to tell you like where you are seeing like more, more or less time spent in the system. And you can see it sort of correlates like, look, there's a lot of total time was estimated was spent, through this, branch here, which makes sense. I don't know if this may be compiled in a weird way because the fact that this isn't shown at all doesn't really make any sense. But I'm assuming it's because this got collapsed down in some way or something. I don't really know what the compiler did. We haven't looked. But again, you can kind of see like, yeah, in this code is super crappy, which we kind of would expect. This is, makes very good sense. When array misses, it's doing this kind of assignment to a v3. It's not particularly smart about it's doing it scalar, not in the SSE, and blah 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 blah. Right. So we, that makes sense to see that, and so on. I don't know. I tend to not put a lot of faith in this because sampling-based profiles, I don't really know. I don't know that I really trust them. So I tend to not use this view, but I just wanted to show it to you. So what we actually care about here, and what we'll probably be using it for, we're at the end of the stream for today, but tomorrow when we start actually working on optimization, what I actually want to do is go to the microarchitecture analysis. So in here, what we can do is say, all right, hotspots, we don't really care about that. I don't trust you. Anyway, we know it's just that one routine that we're optimizing. It's not a big deal. We're not asking you to tell us, find the trees in the forest kind of a situation or the needle in the haystack. This is more what we want to do, memory access or microarchitecture exploration. So in here, if I say microarchitecture exploration, this is where those performance counters I was talking about come into play. This can tell us stuff like how long were you waiting on instruction decode? How long were you waiting for a cache to come back filled? How many times did you stall on that? How many times did you go to try and issue an ad and there was nowhere to put the ad, so you had to just wait till an ALU finished? These sorts of things, right? And so this is where we can get that information from, right? And I don't actually know. So these are the actual. So this is why. Remember, I said there's a lot of them. This isn't even all of them. Here's an example of some of the things that can count. Right. Like these are all on the chip. It can count these things. It's insane, right? So anyway, if we run a microarchitecture exploration, and we go ahead and let this do its thing. There we go. Now, what we can see is if we look at the way that the trying to think of how to explain this. So now if we look at the way that the CPU was actually chewing through our instructions, then at least if this summary is to be believed, which like I said, you have to take some of these things with a grain of salt, what you can see is, look, here in this breakdown on the back end, part of the CPU, what you can see is how much use were we getting out of our ALUs, okay? And what you can see here is that the ALUs are based off of ports. The way that the Intel architecture works, we've talked about this in Handmade here before. There's port 0, port 1, port 2, port 3, port 4, port 5. 6 and 7 are not as much what we were looking at here, but there's a set of ports, right? And you can see them listed here. Each of these ports corresponds to a certain set of instructions it can execute. Each instruction can be executed on only specific ports that support that instruction. So when we're looking at the performance of the CPU, we have these instructions. They're going through the front end, right? Which is taking the instructions that we give it, decoding them into specific things that can be executed on the ports, handing them off to the ports, and our goal to make sure that a piece of code runs as fast as possible if we're not going to change the sort of actual algorithm it uses, is to make sure that we try to utilize as many ports as possible as often as possible, right? Now, a modern x64 chip can decode 4 instructions per cycle. That's it. So on any individual cycle, there is literally no way you're ever going to execute more than 4 microarchitectural actual true operations. Now, some operations aren't actually operations. Something like a move from one register to another isn't an actual operation. So when we're talking about things like port utilization, there's some things that happen up here in the front end. That's the thing that decodes the instructions, remaps things around, that sort of stuff, right? So we don't really care about that. What we care about is this at the moment, and that's adding things, multiplies, that stuff. That's what's happening, shifts, all that stuff. That's what's happening on these ports. We want to see every cycle several of these ports used. Right? We want to hope that when we look at this thing, lots of ports are being used every cycle. Because if no ports are being used on lots of cycles, right? This number right here, that's terrible. That happens when you stall on memory or something else. So you're literally just sitting around doing nothing. If you only have like 1 or 2 ports used, oftentimes like just one, wrong thing. If you have like 1 port used or 2 port used, that means, well, you're doing work, but that work is like serially dependent. So we can't issue like an add here and an add here and have them going at the same time. We have to wait for like the result of that app before we can do another one, right? When you see 3 or more ports utilized, you are happy days, right? Because that means that you're actually doing a lot of actual work, right? So that's great, right? When we see that we have like a high number of our port utilization percentage breakdowns ends up being in the 3+, we're happy about that. That's what we want to see. We don't want to see a lot down in here, right? So if we take a look in here and we see some excuse me. So if you take a look in here and we say like, okay, 100% of the time was spent retiring slots, right? Like what is that even trying to say, right? And you can see like each of those things, like what I just said, if you hover over this, it says something. So some of those, like that may not really tell you much. You probably need an explanation more like mine. But some of them like this is more explicable, right? Like, pipeline slots, fraction used by useful work, meaning the issued UOPS that eventually got retired. Ideally, all pipeline slots would be attributed to the retiring category, retiring with 1,000% right, whatever. So this particular metric here, right, is just letting us know, it's basically another way of saying we didn't have this problem, right? Because basically what happens is when you issue all these instructions, if you have lots of branching that fails, or if you have a lot of situations where like it thought it was going to do one thing and it actually ended up doing another, you can end up throwing away a lot of work. And so what you don't want to see is that like your actual retire rate was very low, right? Your actual number of instructions that you actually then used, you don't want to see that going down. So in this case, I guess it's basically just telling us like we didn't have a lot of misprediction problems or things where stuff got thrown away, which is good, right? Okay. So when we look at what's actually going on here, the only thing that I don't quite understand when I'm looking at this is like that doesn't add up to the right thing, and this is why I say I'm bad at vtune. So when we look at back and bound, right? Like you would expect to see something that told us we were bottlenecked somewhere, right? So, in this case, it's like you're looking at this and I'm going, well, you don't think I'm front end bound and you don't think I'm back end bound. So, like, what do you think is happening? And so I'm not sure I understand it, right? And another way to say that is like, because I'm not, I don't normally use it, vtune. When I look at this and I look at the port utilization here, right? And I look at the breakdown of that number. So it says like the port utilization is like, something like 50% total, right? Like the divider's at 10.5 and the 20. Let me just look at that number, right? So I have 29.8 plus 10.5. That's like 40%. I don't understand why I'm only seeing that and it's not telling me where the rest of it's going, right? And so, we can look up here, cycles per instruction retired. That's a weird metric. I usually like to think of it the other way around, right? Which is how many instructions per cycle I did retire. So if we invert that number, we get 3.2. That suggests to me that, like, again, this number is really the number that should have been, like, shouldn't that be, like, close to 100%, right? Because what I don't understand is, like, if this is our actual CPI rate, where's the extra clocks going? So I don't know. I've always had this problem with Intel V, so I don't use it. I mean, I should use it more because it's, that way I don't have to go over to a Linux machine to do the sampling. But so I often have this problem where it's hard. I don't understand how they're choosing to probably, like, stuff like this always confuses me. I have to manually write it myself. Then I see that it's like, oh, it's close to 4, which is the maximum you could possibly get. Yet these numbers don't suggest the same thing, right? This should be like 90, right? So I get confused about that, right? I just don't know. So, we'll push on this. Maybe before tomorrow, I'll take a look at some of the docs for vtune and try to get a little bit better at understanding those. But that's what we're looking at, right? Now, similarly, like I said before, and we can set which things we want to look at there as well. I believe there's a way. So if you go into microarchitecture analysis, I think you can do something that allows you to get access to this. I just forget what it is. So I really just can't remember how you unlock that. Maybe you have to buy the season pass. So I don't remember how you get this thing to turn on. Oh, do I have to run it in a special mode? I don't know. We'll look this up before next time because I would like to know. Because I basically have to get to the point where I can do the same thing I do with Linux Perf on this if we want to actually look at stuff. So I'll look it up. But either way, So the other thing you can run in vTune, right, is the memory analysis thing. And the memory analysis thing is just, it collects different data on the run, right? So instead of looking primarily at the performance counters that are about back-end usage and stuff like that, here we can get the information about things like cache misses, right? So here you can see, like, look, here's when you were bound on each of your particular types of, on each of the things that you've actually got. So an L1 cache, L2 cache, the DRAM, right? So this is telling us how our memory profile looks, and as you can see, it's pretty squeaky clean, right? According to this, we basically never miss the cache, in theory, right? So, you know, optimizing for the cache wouldn't presumably help us much here, if this is to be believed. So anyway, you can see why I did all that. That's the isolation process. We now have a clean way to measure the performance of the program. So tomorrow what we could do is we could start making some targeted changes to it. We could see how the profile changes. We can also put in a little counter in here so we can just run the program and see if we get faster or slower. So there's a little bit of that we can do. This just sets us up for success, okay? So you can see why I did that. So we can just take targeted evaluation and we can see by metrics whether we're getting better or worse. Let's go to a brief Q&A, and I'm going to have some lunch. And I want to say that there's some John Blow, Sean Barrett action going on later today, if I'm not wrong about that. So we'll try and skip over to that after this stream is done. Might be a good idea to explain the difference between sampling and instrumentation profilers and how they work on some basic level, and why sampling profiling is not a great idea, despite most people believing and telling you that it's very good. Sure. I'm happy to do so. So you heard me say the hotspot analysis. I showed you that thing, and I said, like, I don't really trust these numbers. Like I said some stuff that was dismissive of the hotspot analysis. Why did I say that? Well, the reason I was dismissive of the hotspot analysis is the hotspot analysis does something called sampling-based profiling. And what that does is it says, look, I'm just going to randomly interrupt this process periodically, and I'm going to see where the instruction pointer is. And I'm going to assume that that is where the program is slow. And the reason for that is because typically you're sitting inside your hot loops most of the time. So if we just go ahead and see where you are most of the time, periodically, that should tell us where you're slow. This is not a bad idea in principle. And if it's hardware assisted, meaning your hardware has good capabilities for collecting IP logs without actually affecting the runtime of the program, which actually x64s do for certain things, for branches, for example, it can be okay. I don't know that vTune actually does any of that. I think vTune literally just interrupts your process periodically. I could be wrong about that. So as a result, it's actually not a very good measure for the performance of the program because it's actually changing the way the program runs quite a bit. It's just not a great way to look at it. So the way that we do profiling on Handmade Hero and the way that we'll do profiling here for our actual speed is we just use RDTSC around the block we're trying to time, right? And you've seen me do that multiple times. That's how I like to find hotspots. Now, again, like I said, hardware-assisted sampling-based profiling is not necessarily a bad idea. But I don't really trust vTune's hotspot profiler, so I don't use it. And it's because I just don't trust the sampling that does. So sorry if I didn't explain that. vTune organizes those metrics by something called the top-down performance analysis methodology. There's a pretty detailed paper that introduces this that would likely help. Maybe. I'll take a look. Have you ever tried using Clang CL? It's a drop-in MSVC compatible compiler. There's much better code gen than MSVC CL. It's compatible with link.exe, but even LLD link will give you usable PDBs. When I tried it, my ray tracer, it ended up being 15 times faster than with regular MSVCL. That sounds like your ray tracer was a little bit busted, but okay. Have MeowHash The distribution for MeowHash compiles on both Clang CL and MSVC. I would caution you to... So the thing you said, which is it has much better code gen than MSVCL, is false. So Clang CL has better code gen for some things and worse code gen for other things. So, for example, Clang CL compiles MeowHash worse than MSVCL. MSVCL is better. The MSVCL compiled code is faster than Clang's. That's just how it is. So I would caution you to say, like, Clang CL is not better than MSVCL. It's different. And if you really want to know which one compiles your code faster, you have to test it. Some code will compile much faster on Clang CL. Some will compile much better on MSVCL. One thing that I can tell you is Clang CL is a minefield of undefined behavior nonsense. One of the reasons they do better code gen sometimes is because they screw up your code and introduce a bunch of bugs, right? So I would also say be very careful of that. Clang CL is very bad at being trustworthy about producing good quality code, because anytime they can use a UB trick, they do, which will introduce like security bugs or regular bugs and so on. And so I would just warn you about that. So Clang CL, yeah, not bad. I have used it. It's totally reasonable. It's not better than MSVL. It's different. Sometimes it compiles code better. Sometimes it compiles code worse. And you could pick the one that seems to be better for your project. Games like CSGO go up to 300 frames per second. Are they pretty good optimized? Seems like getting Handmade Hero up to this would be hard. Actually, getting Handmade Hero up to this would be trivial. You just put the raycasting on the GPU or pre-compute the lighting. So, you know, Counter-Strike Go doesn't have real-time lighting. You know, it doesn't do that. All the indirect lighting is baked. So they just don't run that pass. And hey, if we just pre-baked the lighting of Handmade Hero, that would just go away. And currently that's where all of our time goes, basically. If we wanted to speed up the render side of things, there's many ways we can do that as well. So 300 frames per second on Handmade Hero would actually be pretty easy, if that makes sense. Oh, we left an extra... You're right, we did. Thank you for that catch. What's the status of MeowHash? Will it be reaching a new version soon? Probably we will release an 0.6 sometime soon, yeah. I just haven't had time to do so. 0.5 is still, I think, the best hash that there is. It's a very fast hash, and it's much more secure than any of the other non-cryptographic hashes you can use. So, I think 0.5 is already great, but 0.6, you know, we're just trying to finalize a few things so that we can call it standard. Have you tried debugging why the stream loses so many frames when you move the character around? It's just because I'm recording... it's just OBS being dumb, you know. It's got a hard job to do. It's got to record video and stream video, and it just can't handle recording and streaming at the same time at 60 FPS. Because the stream, I think, goes out at like 30 FPS or something, right? What should MeowHash not be used for? There's a very, very clear explanation if you want to know about that. So this page, MeowHash is by Jacob and myself, and this is No Hack Coder is Jacob. Um, this page explains explicitly what hash levels are, right? And basically, like, meow hash is a level 3 hash. Level 4 and level 5 hashes are like what you would typically call cryptographic. Well, level 5 hash really is what you would typically call a cryptographic hash. So that's one where you need it to be very strong against adversaries who know the seed, for example. Level 3 is a reduced level of security, but it's not like most hashes that are non-cryptographic are like this, right? They're not even this. Most are like this. They might not even be level 1 sometimes. But anyway, so in the case of a level 3 hash, what it basically tries to guarantee is that if you use it, an attacker who doesn't know the seed can't generate a collision, right? And, you know, it's based on probabilities and stuff like that. So, you know, you have to figure out like, oh, okay, what was the bit depth and all that sort of stuff. But a level 3 hash is basically a hash where if an attacker doesn't know the seed, they cannot generate a collision. You can't, and meow hash is one of those. You can't, for example, use that kind of a hash for something like digital signatures. Because in that case, everyone knows the seed. The seed's public. So in the case where the seed is public, you can't be using something like a level 3 hash. You'd have to use something like a level 5 hash, right? What you can use a level 3 hash for is anything that might have an adversary still, but where the seed isn't known. A hash table at the front end of a server, for example. There's been a lot of denial of service attack kind of stuff that happens because people used a crappy hash, and the hackers figured that out and were able to craft all their packets to hit the same line of the hash table, which takes down the server, right? Similarly, you can use it for something like message, what are they called? Max message authentication. Like, it's for like message authentication codes between two people, like stuff like that. You can use it for that. So there's a lot of uses for meow hash because it's a lot better than a normal non-cryptographic hash. And it's the fastest hash. So it's faster than all the other non-cryptographic hashes, and it's stronger than them. But it's not a cryptographic hash. So you can't use it like the kind we typically call a cryptographic hash. You can't use it in circumstances where you circulate the key, the seed. Are you sure the hash is secure? People have previously pointed out some issues with meow hash generating collisions. Yes, we're quite sure it's secure. So nobody's ever found a collision in meow hash 0.5 that wasn't standard birthday paradox. So basically the 128-bit, the full 128 bits meow hash, no one's ever found a collision, ever, in 0.5. And in if you just look at the bottom 64 bits, you would expect to be able to find collisions if you tried. If you look at the bottom 64 bits and you try more than 4 billion random attempts, then you should start to be able to find collisions based on the birthday paradox, right? It's very hard to do that because you need a machine with a lot of memory to do it. But it was recently done. And we performed better than anyone else on the test, amusingly. So you can actually look at it here. So here you go. So our old version, which was not a level 3 hash, you can see that there were collisions when you run randomly 100 million hashes and check if any of them collide with each other, right? For 0.5, we were actually below the expected rate and that's basically as low as anyone got besides, like, I guess XXH64. But this is, but we're basically the same, and that's a meaningless number because it's really just random. It should only be, it just has to be at like the birthday paradox level. So that's if you only use the bottom 64 bits of meow hash. If you actually use the whole 64-bit, 128 bits, no one's ever found one, right? So yeah, so meow hash 5 is so far rock solid. No one's ever found a collision in it. And if you go looking for collisions in the low bits by truncating them down to a point where you know you should be able to produce collisions in any hash, even a cryptographic hash, we perform exactly like a cryptographic hash in that case. We produce exactly the expected number of collisions. What do you use meow hash for? Everything. It's like the only hash function I use now. Would Handmade Hero run a 32-bit system or it needs some porting? It probably needs a little bit of porting, right? Even security. Well, like I just said, I don't use meow hash for public message signing, but I don't write any code for public message signing. So the things that I wouldn't use, the things where I would need an extremely strong cryptographic hash, where you can circulate the seed, I don't have that case. But yeah, meow hash, we believe it to be secure for the specific case we talked about, which is if you are not circulating the seed, then we believe it is a strong hash. Oh crap. Yeah, we didn't finish this. I'm glad people in the chat are watching. Thank you. Is Meowhash cross-platform? That's one of the things we're putting in 0.6. So it is in the sense that for ARM and x64, they both have acceleration for AES. So you get very good performance on those platforms. PowerPC, I don't have. So I don't know anything about the performance profile on a PowerPC. I just have no idea. We're not targeting that, and we really don't care. We basically only care about consumer hardware. That's what it's for. So I don't care what it runs like on a PowerPC, but that said, it might be fine. I don't know. Anything that has AES support in hardware, which is a lot of hardware these days, can be accelerated on Meowhash quite a bit. Anything that doesn't will be slower. But how much slower? Hard to say. Any reason we're not using the checkerboard rendering? Yeah, just because I think we're fast enough without it. So I don't think we're gonna need it. Are you talking about our lighting? We did the checkerboard lighting thing, and then we turned it off. Is that what you're talking about? Or you're talking about something else? You're talking about actual checkerboard like rasterization or something. You know, I'm over time anyway. I should go. All right, so I'm gonna wind down the stream here, right? And I don't know what's going on with the stream. So this specifically says like 3 p.m. Pacific time, which is like 30 minutes from now. John and Sean are supposed to have a stream. So it's not up yet, but yeah. Rational coder. You use meow hash for normal hash tables in your everyday code. Oh, absolutely. Yeah. All right, so I'm not hearing anything about when this is going up. So look, here's the thing. I don't really know exactly what's going on, but in theory, in 30 minutes, there should be a stream with John and Sean talking about compilers. If you like the one that John and I did, then this is more of that. So you should check it out. I don't actually know how to make it easier to get to it, but twitch.tv/naysayer88, or go to Twitter, Jonathan Blow, and watch that. That's about all I got. So please check that out. I'll try to raid the channel after, but I'll be honest, I don't think that's going to work, because since they're not live, people probably won't stay there. But so I was kind of hoping that they were at least running a nominal stream. So anyway, thanks for joining us for another. Thanks for joining me for the episode of Handmade Hero. It has been a pleasure coding with you as always. I'm glad we got a little test app set up. Tomorrow we can start to tweak that and actually take a look at the performance characteristics of our Raycaster and optimize those to where we think we need to be. That's it for today. Until tomorrow, have fun programming, everyone, and I'll see you on the internet. Check out that John Blow, Sean Barrett stream if you get a chance. Should be happening at 3 p.m. Pacific Standard Time. Again, that's a half hour from now. The web address for that should be twitch.tv/naysayer88. All right, take it easy, everybody.